Hey, so let's do our test review, huh? All right. So this is, of course, the test review for test 3. And in that review, come on, wakey computer. In that review, we covered chapters 6, 7, and 9, and a chapter on ray optics in night, our supplementary text. And if you don't have the supplementary text with you at home, then I provided links to hyperphysics on the website for you to look at. We covered, in chapter 6, we skipped the vector potential, and when we covered the transformation of E and B fields from moving to stationary frames and back and forth, then we only covered the non-relativistic stuff. So in your textbook, they cover it from a relativistic standpoint, but since I can't assume that all of you had Modern Physics 1, I didn't do that, and we covered the non-relativistic bit. I scanned in the pages from night so that we stuck with non-relativistic systems, so make sure that you look over those. They're on your website. The format is going to be the same as the format of the test last time. So there's going to be 7 total questions, and they're going to be broken into a multiple choice section, which is 6 questions, and then a longer answer section, which is just 1 question. These have separate links on your website. The Respondus Lockdown browser is going to be required for the multiple choice section, and then not required for the long answer section. You'll have 1.5 hours for the multiple choice and then 1 hour for the long answer. It's going to be open for 48 hours starting on Tuesday at 3 o'clock. If you want to earn partial credit for your multiple choice part, just like last time, you're going to have to upload your work and take an image of your work in some way and upload it. And you do that imaging on the long answer part, which is the second link for the test. 1.5 hours for multiple choice, 1 hour for the long answer. Yeah. If you don't upload any work, you're not going to get any partial credit for the multiple choice part. I've posted some practice questions, and then that's for the multiple choice part. Of course, it reviews a lot of good topics, but the long answer is going to be more like your homework. So make sure that you understand everything that's in the homeworks and in the practice questions. The practice questions aren't necessarily comprehensive, okay? They don't cover relativistic, transformations of E and B fields, for example. They don't cover that. I think they get most else, but they can't cover more involved questions, more involved theory. Of course, it has to be open notes because I can't watch you. But the Respondus Lockdown browser does prevent you from switching out of the browser when you're on the multiple choice section. So make sure that you have any notes that you want to look at before you start. And let's see, anything else I want to say? The time on those, it's a timed test. So you have 1.5 hours from the time you start. So that's not 1.5 hours total logged in. So if you start and then you leave and you go eat lunch and you come back, you've lost that time, so don't do that. But the Respondus Lockdown browser does have a little safety feature built in so that if you have to exit for a power outage or your internet goes out or something like that, it'll tell me that happened, and then we can work together to find a solution. Okay, let's launch into the material. I'm going to go really fast through this, but remember, all these lectures are posted online, so if you're confused about any given point, you can go back and look at those notes or that lecture. So we're talking about mostly magnetic fields, starting with chapter 6, and then electric and magnetic fields coming together to make light in later chapters. So the SI unit of the magnetic field is called the Tesla, and the CGS units are the Gauss. There's 10 to the 4th Teslas in a Gauss, or 10 to the 4th Gauss in a Tesla, sorry about that. And magnetic fields can be caused by currents, moving charges, changing electric fields, and magnetic materials. So we had a number of different ways of finding the magnetic field from sources. So the first that we introduced, we did things a little out of order compared to your textbook, but the first thing that we introduced was the Biot-Savart law. And the Biot-Savart law is nice because it gives you the direction of the magnetic field. The other ways to do that, like Ampere's law, for example, don't give you a direction, they just give you a magnitude. So make sure that you use the Biot-Savart law to find the direction. So for a moving point charge, for example, just one charge, the Biot-Savart law says that the magnetic field B is equal to mu naught over 4 pi times QV cross r hat over r squared. So remember, mu naught is the permeability of free space. That's 4 pi times 10 to the minus 7 in SI units. Q is the charge, V is the velocity vector for the moving charge. R is the distance between the charge and the point in question, and r hat is the unit vector that points from the charge to the point in question. Now it's a vector cross product, so this definition includes the right-hand rule. So there's two forms of the right-hand rule. The first is the gun, right? So here you would have QV being your index finger, r hat's your middle finger, and B is your thumb. So QV cross r hat is B. Okay, so that's the right-hand rule for one, and you have to move your hand all around in crazy directions to contort it. The other one is stop in the name of love. So in that one, you hold your right hand out like this with your thumb sticking at a right angle to your fingers. And then you point your fingers along the direction of the first vector, which would be QV here. You swing your palm so towards r hat, and then your thumb would be your magnetic field vector there. It's really important that you know how to do these various right-hand rules and that you understand how to do vector cross products. Now, if you have a bunch of moving charges, of course, you have a current. That's another form of the Biot-Savart law. So here, B, the magnetic field, would be equal to mu naught over 4 pi times the integral of I ds cross r hat over r squared, where I is the magnitude of the current. ds is the little differential unit vector that points in the direction of the current, okay? R hat is the, again, unit vector that points from the place on the wire that you're looking at to the point in question, okay? And R is the distance from that point on the wire to the point in question. So you have to integrate this little dB form that's on the slide in order to get the total magnetic field, okay? Now this is the field that's external, this is the field caused by that current, so that if there's some external magnetic field too, then you would have to add that in. It's not covered if there's an external magnetic field there. Okay, another thing, one of Maxwell's equations is Gauss's law for magnetism. The deal is that magnetic fields, when they're formed from moving charges or currents or changing electric fields or what have you, they don't form diverging fields. They always loop back on themselves. So this is very different from electric fields. And so that means that if you have a closed surface and you integrate the magnetic field lines over that closed surface, that your net flux will be zero, because any magnetic field lines that leave the surface are always going to come back around and loop back through. And so that just tells you that there's zero divergence of magnetic fields as a whole. And you can put this in its differential form here, and using some Calc 3, I'm not going to go through it, and you can say that del dot B is equal to 0. So remember, that's the definition of the divergence of your vector field B. That's going to be 0. And this is just because there's no magnetic monopoles. So there are monopoles for charges. We can isolate positive charges and we can isolate negative charges, but we can't isolate north and south poles of a magnet. Okay, Ampere's law is another way that you can find the magnetic field due to, say, currents. And we have the Ampere-Maxwell law if you want to find the magnetic field from currents and changing electric fields. But Ampere's law is just the current part. Ampere's law in its integral form says that the integral of B dot ds around a closed loop that encircles some current is going to be equal to mu naught times I enclosed, where I enclosed is the amount of current that's enclosed by the Amperian loop, okay? Now, if you want to put that in terms of the current density, J, remember the current density is the current per unit area, then it would be the integral of B dot ds is equal to mu naught times the integral of J dot dA, okay? And here the integration of the area on the right-hand side of the equation would be the area that's enclosed by your Amperian loop, okay? So on the left-hand side, you're doing a line integral. On the right-hand side, you're doing a surface area, okay? Now, if you put Ampere's law in its differential form, then that looks like del cross B, or the curl of B, is equal to mu naught J. So basically, the curl of the vector field is equal to some constants times the amount of current that you've enclosed again, right? The current density that you've enclosed. So you should make sure that you know magnetic fields for certain geometries that are super common. If you are outside of a long straight wire, for example, then the magnetic field for that is mu naught I over 2 pi r, where I is your enclosed current, r is the distance from the center of that wire to the point in question. Current loops, if you're in the center of a little current loop, remember that the magnetic field for that is mu naught I over 2r, where r is the radius of your loop. For solenoids, your magnetic field is equal to mu naught n(I), where n is the number of turns in your solenoid per unit length, okay? And then I is your current. And I think toroids, right off the top of my head, I think it's mu naught I over 2 pi r, where r is the radius of your toroid, okay? Now, remember your alternative right-hand rules for for these things. For long straight wires, if you point your thumb in the direction of the current, then your fingers are going to curl in the direction that the magnetic field naturally encircles that long straight wire. So for a long straight wire, magnetic fields make loops around the long straight wire. For current loops, the magnetic field looks very similar to the magnetic field for a bar magnet, as it does for a solenoid, okay? Except that solenoids, if it's an ideal solenoid, in the interior of the solenoid, if you curl your fingers in the direction that the current flows in that solenoid, so say if you're looking down on it and it goes counterclockwise, then your magnetic field would be inside the solenoid, the direction of your thumb. And then just outside the solenoid, the magnetic field is effectively 0 for an ideal solenoid, which is infinitely long, okay? If you've got magnetic and electric fields, they can exert forces on charged particles via the Lorentz force law. And the total force is going to equal to QE plus QV cross B, okay? So the F equals QE, that's the force from the electric field, and the QV cross B is the force from the magnetic field contribution. And remember that magnetic fields don't exert forces on charged particles that are not moving, okay? They have to be moving in order for that magnetic field to exert a force. Now, if you have basically no electric field, the electric field is 0, and you have a particle that enters a region of uniform magnetic field that is perpendicular to the velocity, then you're going to have your particle making circles in that field. And that's because, of course, F is equal to QV cross B, and a vector cross product is going to be perpendicular to both of the vectors that went into the multiplication. So that means that the force on a moving charged particle in the magnetic field will be perpendicular to its velocity, in addition to being perpendicular to the magnetic field. And if you have a force that's perpendicular to a velocity, you get circular motion, okay? So you set the magnitude of your magnetic field force. Remember, the magnitude of a vector cross product is QVB sine of theta, but if you're assuming that it's perpendicular, then the sine of theta portion would go to 1. And so you have QVB is equal to mv squared over r, which is your centripetal force, and then you can solve for the radius. And this is useful in mass spectrometers and devices like that. Now, if you have a velocity that has a component that's perpendicular but also a component that's parallel to the magnetic field, the parallel component of the velocity with respect to the magnetic field will not be affected. And so your charged particle will still travel along the magnetic field line unaltered there, okay? And then the part that's perpendicular will cause a circular motion. So you're going to then end up with a helix. And remember a little bit of nomenclature here. Your helix, when you have a helical path, they call the distance between adjacent points on the neighboring coils there, they call that the pitch. So for example, if you're going from one circle to a neighboring circle, the distance in between neighboring circles is the pitch. All right, another topic we covered was the Hall effect. And the Hall effect is when you have a current-carrying conductor placed in a magnetic field, that what happens is the charge carriers in that conductor feel that F is equal to QV cross B force. And when that happens, they move in the conductor so that the, so for example, in the figure here, if your current points this way, this is the direction of positive charge flow, then your positive charges QB cross B would be pushed to the top of this bar, and the negative charges, if there are any, anyway, the positive charge would be pushed to the top of the bar. That causes a separation in the charge, okay? And so since the charge is separated, then there's an electric field that's established in the bar, okay? Now the electric field is going to cause a force on the charged particles that is opposite to the direction of the force from the magnetic field. So what happens is charge will build up until an equilibrium is reached. And at that point, no more charges will then move through undeflected. But at that point, you have a voltage that's been created within that, and we call that the Hall voltage. And you can measure it pretty easily. The Hall voltage, which is delta VH here, is equal to the drift velocity, or how fast your charged particles are moving due to the current V sub D, times the magnetic field B times the distance or the width of your bar D here. And you can write that in terms of your current density if you'd like, and you can write your drift velocity in terms of your current density, and that's J over NQ times BD is equal to your Hall voltage. Remember, J is the current per unit cross-sectional area, N is the density of charge carriers that you have in your material, or the number of charge carriers per unit volume, and Q is the charge of a single charge carrier. So that's your Hall effect. We also covered the fact that electric and magnetic fields are just flip sides of the same coin. And what I mean by that is, of course, you have moving charges that create magnetic fields. But let's say that you transform into a reference frame where, like say from a stationary frame, it looks like the charge is moving, right? And then you transform until you're moving with that charged particle. So the particle thinks it's stationary. And it would say that it's not established a magnetic field, but an electric field because it is a charged particle. So since they're so closely intertwined, really it's flip sides of the same coin. So let's say that we define our reference frames this way. S is a stationary frame, and then S prime is a moving frame. Now these frames are inertial. In other words, they're not accelerating with respect to one another. It's a constant velocity transformation from one frame to another. Then you can write the magnetic and electric fields from the perspective of a moving frame. We'll call those B prime and E prime, in terms of the electric and magnetic fields that would be from a stationary observer, which we'll call B and E. If you do that, the transformation equations are as follows. B prime, that's the magnetic field from the perspective of the moving frame, is equal to B minus 1 over C squared times V cross E. Of course, here C is the speed of light, 3 times 10 to the 8th meters per second. V is the velocity of the moving frame, and E is the electric field in the stationary frame. Okay, you can write your electric field from the perspective of the moving frame, E prime, and that's going to be equal to E plus V cross B, where of course E is the stationary frame's electric field, and B is the magnetic field from the stationary frame's perspective, and V is the velocity vector. Okay, so please make sure that you can do a cross product. Okay, make sure that you know the equations for vector cross product magnitudes, QVB sine theta. Make sure you know the right hand rule, and make sure that you can do the longhand form of a vector cross product where you expand it out in terms of the vector components. Okay, make sure you can do all those things. You're going to have to do it on the test, and here we go. So I've given you a few links here to look stuff up if you need a refresher course on how to do cross products. Dot products too, of course, but they're less important on this test than cross products. There are a lot of cross products in the material. I've covered a bunch so far. Okay, moving on to a new chapter. We talked about induction. Excuse me. Electromagnetic induction. And so that's Faraday's law. And Faraday's law of induction states that you can induce an EMF or an induced voltage in a circuit by changing the flux, the magnetic flux through that circuit. So you can induce a current or a voltage via a changing magnetic flux. So mathematically that says that the EMF, curly E there, is equal to minus N d phi b dt, where N is the number of turns in your loop of your circuit, and phi b is the magnetic flux, which is the integral of b dot dA, and then you're taking the time derivative of it. So you can expand that. Of course, the EMF is just a voltage, which is related to the electric field via the EMF is equal to the integral of E dot ds. Remember that there's no minus sign in an EMF induced from Faraday's law. We talked about that in another lecture. So the EMF is equal to the integral of E dot ds, which is equal to minus d phi b dt, which is minus d dt of the integral of b dot dA. So that is the integral form of Faraday's law. Now in differential form, then del cross E is equal to minus partial of B with respect to T. So that's the differential form. So you can induce an EMF by having a magnetic field that changes with time. And that can happen, say, if you have a source of current that changes with time. You can also change the area of the loop with time. We covered a rod sliding on rails, motional EMF, stuff like that. You can also change the angle between the magnetic field and the normal to the loop, and that's more like a generator. You can do that. And then any combination of that will also induce an EMF. Now the minus sign in Faraday's law has become known as Lenz's law. And Lenz's law says that the induced current in a loop is in a direction that creates a magnetic field that opposes the change in the magnetic flux through the area enclosed by that loop. Another way of saying this is that there's a back EMF that's being generated that opposes change, okay? So the induced current wants to keep that original magnetic flux through the circuit from changing. So since there is such a thing as back EMF that opposes change, then there is self-inductance and mutual inductance, and that's how we create inductors in a circuit. So B fields are generated that oppose change of magnetic flux via a back EMF, and this induced or back EMF is always proportional to the time rate of change in the current. So your back EMF is stronger when you have a higher time rate of change of your current. So you can call this back EMF that's generated minus L di dt, okay, where L is the self-inductance of the object, okay? It depends on the geometry and other physical characteristics like the number of turns. You can also have, for example, if you have, so that's self-inductance, right? And you can also have mutual inductance, so that if you have two coils, for example, and you have a current flowing through one that's maybe changing in some way, then it can induce a back EMF in a neighboring coil. Okay, so that's mutual inductance. So these are similar ideas. If you have a self-inductance for an object, you can solve for that using this equation. The self-inductance L is equal to N times phi B over I, where N is the number of turns, phi B is the magnetic flux, and I is the current. And the SI unit of inductance is the Henry. So if you buy inductors, then that will be the units that they're given in their strength in. And of course, mutual inductance, I talked about that. Usually the symbol for mutual inductance is a capital M, and the EMF for, let's see, if current 1 varies with time, the EMF induced by coil 1 in coil 2 is EMF 2 is equal to minus N2 d phi 1 2 dt, which is equal to minus M1 2 di 1 dt. Okay, so the ways that you, and there's the equation for the mutual inductance. It's important to understand that whatever the mutual inductance is for coil 2, it would also be the same value for coil 1. So here the mutual inductance 1, 2 is equal to N2 times phi 1, 2 over I1. Okay, so you did some homework questions on this, and there were some examples that you should look at. But the way to find the self-inductance or the mutual inductance, the procedure is pretty much the same, is to find the magnetic field first, if you don't know it already. If you do know it already and you're asked to find the self-inductance or mutual inductance, you can skip straight from your known expression for the magnetic field to finding the inductance to save time. But if you don't know it, you can usually use Ampere's law to solve for it. And then you can find the magnetic flux using the magnetic field that you found in part 1. So the magnetic flux would be, of course, the integral of B dot dA over the area of your object. And then you find the self-inductance or the mutual inductance using the equations that I've already shown you. That would be N phi over I, okay? N's the number of turns and I is the current. And you shouldn't have, that's to say, shouldn't have current in your expression. I'm sorry about that. It should be canceled out. So the self or mutual inductance should be independent of the current. Sorry about that typo. Of course, if you have an inductor in a circuit, you want usually one with a pretty decent self-inductance, and we call those inductors. And usually what we hope is that while you still have a circuit, and the circuit itself is going to have some back EMF generated from inductance, but the inductor's self-inductance should be larger than that of the circuit. So the inductor will dominate, and you can ignore the self-inductance of the circuit with respect to the self-inductance of the inductor. The symbol for that is the little curly line there, as shown. And then we did some RL circuits. So here you have an RL circuit with a battery, some switches, an inductor, and a resistor. So this is a nice way to look at it. Of course, if S1 is closed and S2 is in position A, then you have a battery hooked up in series to a resistor and an inductor. And then if you close switch 2 to position B and you open switch 1, then you have just an inductor and a resistor in series with one another. Okay? So let's say that you've got your battery, resistor, and inductor, and you close the switch. Then what will happen is that the inductor will at first have a very strong resistance to the flow of current. It's going to generate a very large back EMF initially because that's when the rate of change of the current is largest. And so your current as a function of time will start off at 0 and it'll exponentially increase towards what it would be like if there were no inductor there. And the expression for that is I of t is equal to the EMF of your battery divided by the resistor R times 1 minus e to the minus t over tau. Tau is the time constant of an RL circuit, and that's equal to L over R. So physically, in a battery or in a circuit with a battery, that would be the time for the current to reach about 63% of its max. Now, if you have a nice steady current, then you've had that switch to the battery closed for a long time, but then all of a sudden you switch off your battery, moving it to that other position, for example, the switch, then what would happen is that inductor would then try to maintain whatever current was flowing through it, okay? And it wouldn't be able to succeed forever, but you'd have a current that decays exponentially, okay? So I would be equal to I naught times e to the minus t over tau again, okay? So it would decay off from whatever the current was right when the switch was thrown. Okay, so summarizing, you've got current in LR circuits that's exponential, similar to capacitors. If you combine inductors in a circuit, then it obeys similar equations to those of combining resistors. So if you have series inductors, they add up to find the equivalent inductance. And parallel resistors, you take the inverse, add the inverse, and then take the inverse again. So it's the inverse of the addition of the reciprocals, putting that in English. Inductors store energy. That's how they're able to power circuits very briefly without a battery. And so the energy stored in an inductor is actually stored in that magnetic field. So the energy stored in an inductor with a current I flowing through it would be U is equal to 1/2 Li squared. Now, from that, we derived an expression for the energy density for magnetic fields that's completely general. So energy is stored in electric and magnetic fields. The energy density, which is the energy per unit volume stored in those fields, for the magnetic field U sub B, that's the energy density, is equal to 1/2 times B squared over mu naught. And the energy density for electric fields U sub E is equal to 1/2 epsilon naught times E squared. Okay, so that's the magnitude of those magnetic and electric fields there. Okay, then we talked about displacement currents. Basically, a displacement current is just when you have a changing electric flux. And that can create a magnetic field too. So the integral form of the Ampere-Maxwell law is the integral of B dot ds about a closed loop, an Amperian loop again, is equal to mu naught times I enclosed plus mu naught times I displacement. And the displacement current I sub d is equal to epsilon naught times d phi e dt, where phi e is the electric flux. Remember that the electric flux is the integral of E dot dA over the area. Okay? So if you were to put all of that in terms of its differential form, then the Ampere-Maxwell law would read as del cross B is equal to mu naught J plus mu naught epsilon naught partially with respect to T. So you can see from this equation that currents cause magnetic fields, but so do changing electric fields. So Maxwell came up with the idea of the displacement current, and then using that, he sort of unified the four equations that govern electricity and magnetism, which are, of course, Gauss's law for magnetism, Ampere's law, and Faraday's law. So those four then became unified. And from those four equations, well, specifically the Ampere-Maxwell law and Faraday's law, you can solve those simultaneously to show that light is an electromagnetic wave. This was a huge advance. People knew that light was waves, but this mathematically proved it. He also proved then conclusively that the light in a vacuum travels at the speed of light, c, which is 3 times 10 to the 8th meters per second. So he said light's a form of electromagnetic radiation, and he showed that fields were real things by showing that they could exist in empty space and that light was a self-propagating transverse electromagnetic field. Let me show you here. So that you have an electric field which is changing in time, okay? And then that electric field which is changing in time, remember changing in time electric fields induce magnetic fields, but changing magnetic fields in time induce electric fields. So it's a self-propagating thing. The changing electric field induces a magnetic field, which induces an electric field, which continues on. And he proved that C is a fundamental constant of nature by showing that it was equal to 1 over mu naught epsilon naught. Also, the magnetic field strength and the electric field strength are related to one another. The magnitude of B is equal to the magnitude of E over C. Okay? So light is a transverse wave, which means that its direction of propagation is perpendicular to its direction of oscillation. And all of this is related together in something called the pointing vector, which we use an S to symbolize. And so the pointing vector S is equal to 1 over mu naught times the cross product of E and B. So it's 1 over mu naught E cross B. The pointing vector points in the direction of propagation. And of course, since E and B are time dependent, so is S. But if you take the average value of S over time, then that's equal to the intensity of the wave. And remember that we define an intensity as a power divided by an area. And the intensity is equal to the average value of the pointing vector, which is equal to C times the energy density. Okay? All right. Now, the direction of the electric field vector gives you the polarization of the wave. So here we have, for example, a plane polarized electric field, and it's polarized in the y direction. You can polarize light by absorption, scattering, and all kinds of other ways, but what we focused on, pardon the pun, was the polarization from absorption that comes from polarizers. So for that, you have the law of Malus to describe it, M-A-L-U-S, right? So it says that the intensity that comes through a polarizer is equal to the max intensity of the polarized light times the cosine squared of theta, where theta is the angle that the polarizer makes with the polarized wave. Okay? So the intensity is proportional to a cosine squared of theta. Now, if you have an initially unpolarized light source, the law of Malus is written for light that's already polarized before it enters the polarizer. But if you have unpolarized light, then you can do an average of that, and you can show that the polarizer is going to halve the initial intensity of the light that enters it. So when you pass your light through your first polarizer, its intensity drops by half, and then after that, the law of Malus is obeyed if you pass it through subsequent polarizers. Okay, then we started getting into ray optics, which is from our Knight textbook. And the first thing that we covered was the law of reflection. And basically, the most important thing that you can remember about this chapter is that all of these angles are given with respect to the normal of the boundary. So the angle of incidence has to equal the angle of reflection, but that's the angle with respect to the surface normal. We also talked about the law of refraction. Remember that when light encounters a boundary between media, it can either be reflected or transmitted. If it's transmitted, then if the index of refraction is different in between the media, then it will obey Snell's law. Snell's law says that if you're going from medium 1 to medium 2, that n1 sine of theta 1 equals n2 sine of theta 2. where N1 and N2 are the indices of refraction of medium 1 and medium 2 respectively, and theta 1 and theta 2 are the angles that the light ray makes with the surface normal for 1 and 2 respectively. Remember that the reason that this all happens is because the velocity of light changes as it goes through different media. That is, V is equal to C over N, where C is the speed of light and N is the index of refraction. So when you pass through a medium with some index of refraction N, the speed of light is lowered from the speed of light in a vacuum by 1 over N. Okay, now, you can also have what's known as total internal reflection, and that occurs if you have a medium, you're going from a medium that is, you're trying to go from a medium that's more dense to one that's less dense, or the one that has a higher index of refraction to a lower index of refraction, okay? Then what can happen is that light will not be transmitted through that medium if the angle isn't right. Now, the critical angle is the boundary between when transmission will occur and when it will not occur. And theta critical is the inverse sine of N2 over N1. So if your angle is greater than the critical angle, then you're going to have total internal reflection. All right, we talked about lenses and mirrors and imaging with lenses and mirrors. There's two kinds of lenses. You can have converging and diverging lenses. For a diverging lens, if you have light rays entering a diverging lens that are parallel to the optical axis, then they just split off and go in all directions. And for a converging lens, then if you have light rays that are parallel to the optical axis, then they will be focused to a point. Okay, that point's of course called the focal point. Oh, converging lenses are thicker in the middle than they are on the edges, and diverging lenses are thinner in the middle than they are on the edges. And of course, they change the path of light via refraction. Now, you can do ray tracing, which is drawing of the paths. And in order to do that, you're going to follow the directions for ray tracing and examples that we did in the lectures. So you're going to draw an optical axis, center the lens on that optical axis, and mark your focal points on either side. You're going to draw your object. You can just use an arrow. You don't have to be able to draw. The height of the image, or the height of the object is h. The height of the object is h. The distance of the object from the center of the lens is s. Now what you're going to do is you're going to draw 3 light rays. One is parallel to the axis, one that enters the lens along a line through the near focal point, and one through the center of the lens that goes straight. Okay. Now for converging and diverging lenses, of course, after the light passes through a diverging lens, it's going to broaden out. Converging lens is going to be bent inward. Okay, so just remember all those rules go over for both converging and diverging lenses. I tried to merge them here, but you should go back and look over and make sure that you understand it. Then in the ray diagram, you're going to extend your rays until they converge, and that's your image point. And then you draw the rest of the image in after that. And you measure S prime and H prime, which is the distance of your image from the center of the lens and the height of your image. Using H prime and H, you can find the magnification. The magnification magnitude is H prime over H, right? So it's just how much it's blown up or shrunken. And you can also set the magnification equal to minus S prime over S, okay? Of course, if M is negative, the object's inverted. If it's positive, the object is upright. You can calculate the image placement rather than doing ray tracing if you want, using the thin lens equation, which works for both converging and diverging lenses. It's 1 over S plus 1 over S prime is equal to 1 over F, which is the focal length. If S prime is negative, then the image is on the same side of the lens as the object, and that's a virtual image, okay? You can use the lens maker's equation to solve for what the focal length is going to be. The lens maker's equation is 1 over F is equal to N minus 1 times 1 over R1 minus 1 over R2. Of course, N is the index of refraction again, F is the focal length, R1 and R2 are the radius of curvature of the lens on the near side and the far side of the object. Remember that there's sign conventions. So R1 and R2 are positive if they're convex towards the object, and they're negative if it's concave towards the object. F is going to be positive if you've got a converging lens, and negative if you've got a diverging lens. And S prime is going to be positive if it's a real image on the opposite side of the lens from the object, and it's going to be negative if it's a virtual image and on the same side of the lens from the object. We also talked about how to deal with mirrors. Concave mirrors curve towards the light source. Convex mirrors curve away. We considered only curved mirrors that could be modeled as a section of a sphere. So these are spherical mirrors that we're considering only. So you can do ray tracing for spherical mirrors just like you can for lenses, following very similar steps, except of course the light rays are going to be reflected. They're not going to be transmitted through the lens. The mirror equation and the lens equation are very similar to one another, okay? And the magnification equation is the same. The focal length for spherical mirrors is always going to be r over 2. And the sign conventions are that r and f are positive if they're concave towards the object and negative if they're convex towards the object. And s prime is going to be positive if it's real on the same side as the object. And s prime is going to be negative if it's virtual, opposite from the object. Remember, the convention for the sign for s prime is different for mirrors than it is for lenses, okay? All right, that's it. I know I sounded like a tobacco auctioneer, but it was a lot of material. I hope you found that useful, and remember that just because I don't mention something in the review doesn't mean that it's not important. It just means that maybe I didn't have time to get to it in this tobacco auctioneer coverage. Make sure that you work problems. Working problems is the best way to study for a physics test. And make sure that you understand your homework, any quiz questions, and the multiple choice practice questions I posted. Okay? Good luck, happy studying, and I'll see you around.